In this video we're going to examine a funky mathematical construction called a series to parallel transform that lets us calculate the behavior of arbitrary RLC networks at resonance very quickly. I've drawn this circuit to illustrate why we might want to use a series to parallel transformation on a circuit. We've already worked out the math describing series and parallel RLC networks, but we can't apply that math to this load. Further, that math was kind of a pain that involved a quadratic equation, so having to recalculate the formulas for quality factor and natural frequency for every arrangement of components seems like a headache. However, if we could somehow swap in a model of the capacitor that had the ESR in parallel with the cap instead of in series, this becomes a simple parallel RLC circuit. We can make a parallel model of a component that matches the series behavior, as long as we confine ourselves to one frequency, by making sure the impedance and quality factors of the series and parallel models are equal. This only works at one frequency because the series and parallel formulas are quite different from one another, but it's okay because we often only really care about the behavior of RLC circuits at resonance. Also, note that though I've drawn some schematics here using capacitors, we're going to do our math with a generic reactance to make sure our results apply to inductors too. I've started computing the transformation by equating the impedance of the series combination with the parallel combination here. We're going to need to split this into real and imaginary parts soon, so we have to do some algebra to rationalize our parallel expression. The second step in this process is equating the component quality factors for the series and parallel models. Finally, we can split up the impedance into real and imaginary parts. The imaginary part gives us a relation for the series reactance in terms of the parallel reactance in Q. Now, this expression is interesting when Q is high. Our transform says that we don't need to change the value of reactance for big values of Q. So we'll treat it as the same whether we're in series or parallel. The real part gives us a relation between the series resistance and the parallel resistance in terms of Q. For big values of Q, we see that the series and parallel resistances are related by Q squared. This resistance equation can make resistors look substantially larger or smaller, which captures the underlying physics that current in a capacitive inductive branches of parallel RLC circuits are amplified by Q compared to the resistive branch. This is a useful impedance transformation that we can achieve just by putting a load resistance in series with an inductor or a capacitor, and we'll start using it very soon. So in summary, you can equate series and parallel RC or RL networks at one frequency, which is convenient for analysis. You do that by setting the Z and Q of the series and parallel networks equal, and the resulting equations capture a resistance transform that we're going to make good use of, and I've summarized those equations here.